guys, so we are starting day 5 of lesson 7.1. So this is our second week in the same lesson. Today we're going to get into polyatomic ions and their compounds. Alright, so the first thing we need to talk about is what is a polyatomic ion. You guys probably remember from lesson 6.3 that a polyatomic ion is basically a compound that is covalently bound to each other, but their overall charge is not zero. So if I look at this is ammonia. All of these, the nitrogen is covalently bound to the hydrogens, but their overall charge has a positive 1. This is a polyatomic ion because it is made up of more than one atom and because it has a charge, so it's an ion. Okay? So here are some more examples of polyatomic ions. You need to understand that when a polyatomic ion is positive, that basically means that there is one electron missing from this overall thing. And when a polyatomic ion is negative, it means that there's one extra electron in its Lewis structure that would not have originally been there if it looked a little bit different, right? And of course, if it has a -2, that means that there are 2 extra electrons in the Lewis structure. In general, we're going to be talking a lot about the negatively charged polyatomic ions. Alright, so what we need to understand here is a lot of the polyatomic ions we're going to be talking about are called oxyanions. Oxyanions are negatively charged ions which contain an oxygen. So one example would be nitrogen. We have nitrate and we have nitrite, okay? Nitrate has 3 oxygens and nitrite has 2 oxygens. Both of them have a charge of just -1, but the only way that we can distinguish them by name is that the one with the more oxygens has the 8 and the ones with the less oxygens has the ite. And I want you all to remember that if I wrote nitride with a D, it would only be an N with no oxygens. As soon as you see 8 or ite, you know immediately that there have to be oxygens inside of this ion that we're talking about. So if I ever gave you something like sodium nitrate, that means that we're talking about this, not just N negative, okay? All right, so now here are some examples of polyatomic ions. First thing, if we only have one possible polyatomic ion, like for boron and carbon, then we're just going to give them 8s, okay, ATE. If we have 2 possibilities, like nitrogen, phosphorus, arsenic, sulfur, selenium, and tellurium, the one with more oxygens is going to take the 8, and the one with less oxygens is going to take the ite, okay? And like here, phosphate, phosphite, arsenate, arsenite, sulfate, sulfite, selenium, you get the idea, okay? And now, another thing happens where if we have more than 2 possibilities. Remember, if we have 2 possibilities, it's only 8 and ite, okay? But if we have 4 possibilities, like with chlorine, we have to give them more names. So we can have chlorine that is all of these negatively charged ions, but some chlorines will have 1 oxygen, some will have 2, some will have 3, and some will have 4. So chlorine with 1 oxygen will have hypochlorite. And then 2 oxygens is chlorite, and then we leave the ites, we go into the 8s. As soon as we get another oxygen, we go to chlorate, and then the final form, when we've reached our final form, we go to perchlorate. This is just how you distinguish between different oxyanions of chlorine. And remember, if we have chloride, then that's just Cl negative with no oxygens. As soon as you see ites, 8s, hypos, or pers, that tells you that this is not just a regular ion that I can find in my periodic table. This is a polyatomic ion that I need to find in a different table, okay? So, for example, right here, you can see that chlorine is one of the ones that has 4 possible ions with 1 oxygen, 2, 3, and 4. So we have hypochlorite, chlorite, chlorate, perchlorate. Then we have bromine, hypobromine, hypobromite, bromate, and then perbromate. You get the idea. There's a clear pattern of what is happening here. And overall, they tend to have the same charge. But for us to distinguish between each particular one, we just change the name a tiny little bit. Quick reminder, if you see an IDE, I-D-E, then we're not talking about any of these. We're just going to go for Cl negative or Br negative or I negative. Okay? All right, so here's another table that will show you some more of these commonly occurring ions. So our basic idea here is like the polyatomic ions we're going to be talking about that are positive are mainly just ammonium. We're not going to get much deeper into positive polyatomic ions. The negative ones is where you have a lot of different possibilities. And this is usually because covalently bound compounds like to hold on to their electrons, so they're probably there's probably a lower possibility for them to become positively charged. So now, when we take these polyatomic ions and we combine them with other ions, we can form ionic compounds. So as you can see here, this is chlorate, ClO3, okay? If we had another oxygen, it would be perchlorate. But this is chlorate, and it has an overall charge of negative, which means this whole thing together can bind to something that has an overall charge of positive 1. So when it finds this potassium, which is K, remember, potassium is K, not F, not P, it can bind to it, and together they will form an overall charge of 0 because there's one positive charge and one negative charge, so they cancel each other out. So even these polyatomic ions, they behave in the exact same way that regular anions would behave. They're just trying to find somebody to cancel out their charge, just like the regular chlorides and iodides and all of those, right? And then we have another example. We have magnesium and phosphate, okay? Remember, phosphate is over here. Phosphate, pH, because it's PO4 minus 3, okay? So now we're going to go back here. So we have magnesium and phosphate. We always give the name of the cation first and then the name of the anion. And the name of the anion is not going to be phosphide. We're just going to give the name of the anion from this table that you guys see right here. Okay, we're not going to erase the end of its name and add "ide" in the end. It's just going to be whatever the name you find here. So, name of the cation and the name of the anion. Okay, that's how you name an ionic compound which contains a polyatomic ion. Okay. All right. So now what you need to understand is when these ions come together, say the potassium and the sulfate, nothing about their structure is going to change, okay? So the potassium is going to stay looking like this, and the sulfate is going to stay looking like this. But at no point is there going to be an exchange of atoms between the polyatomic ion and the actual other ion, right? These are going to stay exactly the same. They're just going to be stuck together because the positive and the negative are attracted to each other. Same thing happens here. This is an ammonium. This is a nitrate. When they come together, we don't get two completely different molecules. They just stick together like this.
Okay, so let's try this example right here. Tin 4 sulfate. Now, you guys remember from when we were talking about the stock system that when we get Roman numerals, that means that this particular cation has a possibility to have more than one type of charge. This is why the charge is just given to us. So we got lucky here. SN4+. If you're wondering where I got SN from, you can just go here and you'll find tin down here, which has a symbol of SN. The charge is given to us, so we already know. Now, sulfite or sulfate ends with an ATE, which means we are talking about a polyatomic ion. Now, if it ended with an ide, then all I would need to do is go to the periodic table and find the letter S, and I would find my charge. But obviously, that's not the case because we end with an ate, A-T-E. So in this case, what I need to do is I need to go to this table or this table, whichever one is easier for you to navigate, and I need to find the polyatomic ion that I'm looking for. So in this case, I'm looking for sulfate, so it's right here, SO4 2 minus. So now I'm going to write it like this in brackets, SO4, and the charge goes on the outside of the brackets, okay? This is just going to help you, putting in the brackets is going to help you distinguish between the number of oxygens and the actual charge, okay? I don't want you to touch this. SO4 starts as SO4 and it will end as SO4. You never have to simplify the SO4. It stays exactly the same the entire time. Don't touch the number 4. So now we're going to do the swap and drop. The 2 goes down here, the 4 goes down here, so we end up getting tin 4 plus, but we have 2 tin atoms, right? Remember, in this process, we are just looking for the number of atoms or the number of ions in each one. And then we have SO4 with 2 minus, but now I have 4 of these because the 4 went from up here and went down here, which means that it should look like this. SN2, SO4, 4. Now, even though this looks right, there is only one thing wrong. And the only thing that's wrong is that we can simplify this further. See how there are 2 tins and there are 4 sulfates? We can very easily simplify the numbers 2 and 4 by just dividing each one of them by 2, right? So in the end, we're going to get tin sulfate, SO4, but with a 2 here and a 1 here. And as you guys know, we don't represent the 1, so this is my final answer. Now let's just double check the charges based on this and on this. So we have 2 times plus 4 for tin, plus 4 times minus 2 because we have 4 sulfates, and here we have 2 tin ions, which means positive 8 minus 8 equals to 0. So in the end of the day, at the end of it, the charge is also balanced out. Okay, so guys, now let's try this example. You can see here that sodium does not give you Roman numerals, so to find the charge of sodium, I have to go in here, into my periodic table. I can see that it is in group 1, there it is, Na, so it has a charge of plus 1 for sodium, okay? So Na plus 1. And then I'm going to look at my anion, chlorite. Chlorite does not end in IDE, which means I can't find this using my periodic table. I have to go to this table right here, okay? So let's find it. I can see that chlorite is right here, ClO2 negative, okay? So I'm going to go ahead and write ClO2 with a -1 charge. And if it helps, you can put the brackets here, but you will be removing them later just because of the way the question is going to end up going. So now let's go ahead and do our swap and drop. So this one goes here and this one goes here. So I have sodium plus 1 and only one of them. And then chlorite, ClO2, 1 with a charge of -1. Now I can see that this is already perfectly balanced. I can't really make these 2 number 1s turn into anything less than they are. So my overall substance is going to be like this. Sodium ClO2. Now I don't need to keep the brackets there because I only have 1 chlorite. If you've only got 1 of your anion or of your polyatomic ion, don't leave your brackets in there. Just get rid of them. All right, so now this is my final answer. Let's go ahead and check if our charges make sense. So I have 1 positively charged sodium ion, plus I have 1 negatively charged chlorite. This equals to plus 1 minus 1 equals 0. So my overall charge makes sense. If I have one sodium and one chlorite ion, polyatomic ion, they will cancel each other out and form an overall charge of 0. Okay, so now guys, if you are confused, you can re-watch the video, and if you really need help, message me on Shobi. Go ahead and good luck.